the silent immensity of interstellar space, wanderers occasionally emerge messengers from beyond the sun's dominion, bearing the cold memory of other stars. Most pass unnoticed, their trajectories faint arcs carved through the void. Yet some are different. Some carry the weight of danger. Among them is 3I divided by Atlas, only the third interstellar object ever identified. A fragment of frozen time and alien dust, now threading its way into our solar system. Captured by the Hubble Space Telescope, its pale, ghost-like form stretches across space, its nucleus estimated to span between 0.32 and 5.6 kilometers. Astronomers quickly confirmed, this is not of our Sunday. Its path betrays origins from a distant stellar cradle, yet its future brings it perilously close to a world we know well, Mars. And herein lies the unsettling possibility. In late October, 3I divided by Atlas will swing into perihelion, its orbit slicing through the domain of Mars. Yet, Earth, by a cruel geometry, will be blind to the event. The sun's glare conceals it from our vantage point, leaving spacecraft in Martian orbit as the only reliable witnesses. This celestial stranger, invisible to us at the critical moment, may expose Mars not to collision, but to something subtler and more insidious, the passage of dust and debris. Scientists warn that a storm of particles could seed the skies of Mars with meteors, a dazzling spectacle from the surface, but a dire hazard for orbiting probes. Tonight, we embark on a new journey, where the theme of 3I divided by Atlas might be the worst thing to happen to Mars, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. Now the stage is set. On October 3rd, 2025, Mars will stand at just 0.19 astronomical units, roughly 30 million kilometers from the comet's inbound trajectory. No direct impact is forecast, yet the very sweep of its dusty tail may intrude upon Martian space, brushing the thin atmosphere, scattering fragments across orbital lanes, and threatening satellites that have become the eyes and ears of humanity on the red planet. This is the scenario scientists call the worst case, not of cataclysmic destruction, but of fragile machines enduring a storm of alien dust. To understand why this encounter matters and what it could teach us about cosmic visitors from beyond our sun, we must follow the comet's path closer still toward its rendezvous with Mars. The void between the worlds, so often perceived as an absolute emptiness, is in truth a theatre of delicate and perpetual forces, a domain where gravity pens the only law that matters. On the 3rd of October, 2025, this theatre will host a performance of singular rarity, a pas de deux, choreographed by the cosmos itself. The dancer, an itinerant from a star system beyond our own, known only by its catalogue designation, 3I divided by Atlas, will execute its closest approach, not to our own world, but to the rust-coloured plains of Mars. The distance, a mere 0.19 astronomical units, or approximately 28 million kilometers, is by the vast scales of the solar system, a proximity that borders on the intimate, a whisper in the dark. It is a distance calculated to avoid cataclysm, yet close enough to permit the most tenuous and ghostly of touches, the gentle caress of the comet's immense dust-gas tail against the fringes of the Martian sphere of influence. According to current models of orbital dynamics and cometary behavior, this is a predictable, if notable, celestial event, one that will pass without physical impact, a near miss in the grand orbital clockwork. But what if the concept of an impact is itself a relic of a cruder understanding? What if the true interaction is not one of collision, but of contamination, an invisible infusion of foreign material into a pristine atmospheric system. The European Space Agency has confirmed that its vigilant sentinels, the Mars Express and the Trace Gas Orbiter, will maintain an unblinking vigil from the 1st to the 7th of October, their instruments calibrated to detect the subtlest of whispers from the void. Their primary mission is to monitor the Martian atmosphere, a thin veil of carbon dioxide that is perpetually being sculpted by the solar wind. The data they will gather is predicated on a known set of variables, a controlled experiment on a planetary scale. Yet, the introduction of 3I divided by Atlas introduces a new, unquantified variable. The comet's perihelion, the point of its closest approach to our Sun, falls in late October, placing it within the orbital lane of Mars at a time of immense activity within its nucleus. As ices sublime and are blasted into the vacuum by solar radiation pressure, they carry with them a fine mist of dust, a particulate stream that will, for a brief window, be aimed directly at the red planet. Could this not be the genesis of a phenomenon both subtle and profound, an invisible meteor shower, a rain of dust so fine it would be imperceptible to the naked eye, yet potent enough to act as a catalyst for a cascade of atmospheric reactions we have only begun to theorize? At the first and most conservative level of analysis, this interaction would manifest as a negligible perturbation. A sparse, tenuous cloud of cometary dust would pepper the upper Martian atmosphere, resulting in a minor, statistically detectable increase in micro-impacts. These tiny collisions, occurring at hypersonic velocities, would momentarily ionize the thin air, creating transient pockets of charged particles that would ripple through the ionosphere like stones skipped across a placid lake. The effect would be fleeting, lasting perhaps a few hours, a brief and silent symphony of light and energy played out in a register, detectable only by the most sensitive of instruments. It would be a fascinating data point, a confirmation of the dynamic interplay between celestial bodies, but one that would quickly fade into the background noise of the planet's normal atmospheric activity. But is it not the most subtle of whispers that often portend the most profound truths? What if the initial ripple is merely the prelude to a more significant harmonic resonance within the atmospheric envelope? Ascending to a more substantial hypothesis, we must consider the possibility that the comet's tail is not a uniform, wispy stream, but contains within it denser filaments, ribbons of concentrated material forged in the turbulent outbursts of its nucleus. Should such a filament intersect with Mars, the result would be far more dramatic than a simple increase in particulate counts. We would witness the ignition of a temporary metallic rain as a higher density of cometary particles, many of them rich in silicates and complex organics, ablate in the upper atmosphere. This sudden infusion of metal ions, a form of cosmic pollution, would act as a potent dopant, seeding the ionospheric layers and creating localized plasma anomalies. The smooth gradients of electron density would develop sharp, unpredictable wrinkles. These plasma waves would, in turn, act as a funhouse mirror for the radio signals upon which our orbiters rely, scattering and distorting them, leading to temporary but significant telecommunications disruptions for the fleet of robotic explorers circling the planet. The machines themselves would register these events as inexplicable data glitches, momentary lapses in their connection to the engineers millions of kilometers away. Yet, one must ask, if a mere ribbon of dust can so disrupt our most advanced technology, what does that reveal about the fragility of our communication bridges across the deep? The most speculative, yet most intriguing, scenario posits the formation of a transient, localized hotspot of dust-plasma interaction. This would not be a mere wave, but a veritable storm, a concentrated knot of energy where the influx of cometary material is so intense that it triggers a self-sustaining feedback loop within the Martian magnetospheric environment. The constant bombardment and ionization of particles would create a localized region of highly turbulent and unpredictable plasma, a bubble of chaotic physics clinging to the edge of the planet. The sensitive field and particle detectors aboard orbiters like MAVEN or the Trace Gas Orbiter, designed to measure the gentle currents of space, would be confronted with readings so far outside their calibrated norms that their internal safety protocols would be triggered. To preserve their functionality, their programming would force them into a protective safe mode, a temporary withdrawal from their scientific duties until the anomalous conditions passed. They would, in effect, be momentarily blinded by the very phenomenon they were sent to observe. This is not a failure, but a testament to the limits of our foresight. What fundamental physical processes, currently unknown to our models, might be at play within such an ephemeral and energetic crucible? And what could their transient existence teach us about the behavior of matter in the most exotic of environments? In this grand cosmic experiment, Mars is transformed. It ceases to be merely a world under observation and becomes a vast, planetary-scale sensor, an early warning device for a new class of interstellar interaction. The data painstakingly gathered by our robotic emissaries during this week in October 2025 will become the foundational text for a future manual, a survival guide for navigating the dusty, plasma-rich wakes of visitors from other stars. For when humanity finally ventures beyond the cradle of the Earth-Moon system, on long-duration missions to Mars and the asteroid belt, we will no longer be passive observers of such events. Our ships, and the lives they carry, will be the instruments taking the readings. The silent, invisible rain that brushes past Mars in 2025 could, in a future century, be a gale-force wind threatening a crewed vessel. Therefore, we must ask, are we merely documenting a celestial curiosity, or are we in fact learning the first crucial lessons of how to survive the gentle, yet potentially deadly, the breath of the galaxy? But to truly comprehend the potential of this ethereal touch, one must first seek to understand the source of the breath itself. The gossamer tail, stretching millions of kilometers, is but the ephemeral echo of a solid body, a hidden heart of ice and rock. What, then, is the true nature and scale of the iceberg from which this colossal, shimmering coma has blossomed? It is a shadow that falls not upon the ground, but upon the very foundations of planetary science, a silhouette cast by an object so distant, so minute, and yet so profoundly consequential that its mere passage forces a fundamental re-evaluation of our cosmic neighborhood. The object designated 3I divided by Atlas, an interstellar vagrant passing through our provincial star system, presents a paradox of scale, where its true physical dimensions seem almost laughably insignificant when weighed against the immense gravitational pull it exerts on our theories. Its influence is not a product of brute mass, but of intense, enigmatic activity, a testament to the idea that the smallest of cogs can, under the right conditions, set the largest of wheels into motion. The central question, then, is not merely one of metric tonnage or radial diameter, but of potential. How vast is the iceberg, the immense unseen bulk of processes and consequences that lies beneath the visible tip of this celestial wanderer? The shadow it casts is long, and within its penumbra, the established narratives of dust, transport, and planetary accretion begin to waver, suggesting that our solar system, for all its perceived isolation, is not immune to the subtle, granular influences from the great dark between the stars. Could it be that the true measure of an object lies not in its substance, but in the disturbances it creates in the fabric of its surroundings? According to the meticulous observations conducted by the Hubble Space Telescope, the nucleus of 3I divided by Atlas is a study in minimalism, a compact entity whose diameter is constrained to an upper limit of less than 5.6 kilometers, with some models suggesting a far more modest, almost pedestrian scale of a mere 320 to 440 meters. This is a speck, a mere pebble on the grand beach of the cosmos, and yet the very same data that establishes its diminutive stature also confirms its vibrant, almost frantic vitality. The Hubble images reveal a crisp, well-defined coma, a halo of gas and dust that can only be sustained by vigorous, ongoing sublimation, a process where the icy heart of the nucleus transforms directly into gas, tearing microscopic grains of dust from its surface and hurling them into the void. The estimated mass, on the order of tens of billions of tons, while substantial, is precisely what is required to fuel and maintain the spectacular dust tail that stretches for tens of millions of kilometers behind it, a shimmering banner announcing its presence. Here lies the first, most fundamental hypothesis. A nucleus, though physically small, can possess an extraordinary level of dynamism, its internal engines running at such a ferocious pitch that it becomes a prolific factory of fine particulate matter, capable of seeding its orbital path with a continuous tenuous stream of microscopic projectiles. If such a modest body can generate such an extravagant display, what does this imply about the latent power contained within the countless other, unseen planetesimals that drift through the galactic voids? This leads us to the first tier of our analytical inference, a contemplation on the relationship between a small but energetic source and its extensive downstream effects. The sheer length of 3I divided by Atlas's dust tail, a luminous river stretching across the interplanetary medium, is a direct and irrefutable testament to the efficiency of its outgassing mechanisms. Each jet of carbon dioxide and other volatile gases, erupting from the sun-warmed surface of the nucleus, acts as a nozzle, entraining countless trillions of dust particles and accelerating them to velocities sufficient to escape the comet's weak gravity. These particles, once free, become subject to the twin influences of solar radiation pressure and gravity, spreading out to form the vast diffuse trail that our telescopes so easily capture. The hypothesis at this initial level is one of sufficiency. It posits that raw size is not the primary determinant of a comet's influence, but rather the specific activity, the mass loss rate per unit area of its nucleus. A hyperactive core, even one of sub-kilometer dimensions, can indeed act as a sufficient and persistent source to nurture a dust tail of staggering proportions, a river of silt flowing from a surprisingly small spring. But does this prolific output, this generous seeding of the interplanetary environment, remain a mere spectacle, or does it possess the potential to touch, in a tangible way, the worlds it passes by? We must then ascend to the second, more consequential tier of speculation, where the diffuse river of dust begins to interact with the architecture of our inner solar system. A nucleus of even moderate dimensions, should its activity be sustained and its trajectory fortuitous, would generate not a thin, wispy stream, but a dense, concentrated plume of particulate matter. As 3I divided by Atlas carved its path through the inner system, this plume would disperse, its constituent particles following their own slightly perturbed Keplerian orbits, creating a wide and statistically significant debris field. The orbit of Mars, a neighboring world, would thus not be a sterile highway, but a potential intersection point for this incoming flux. The probability of a micro-meteoroid, a grain of dust no larger than a speck of pollen, intersecting with the orbital path of the red planet, would increase dramatically, transforming a rare event into a potential shower. These particles, traveling at hypervelocities, would not simply bounce off the Martian atmosphere. They would vaporize upon impact, injecting their mineralogical essence directly into the upper layers of the gaseous envelope. The hypothesis here grows bolder, suggesting that the passage of a single, active interstellar comet can significantly alter the local micro-meteoroid flux for a planetary body, providing a direct, exogenous delivery mechanism for materials that are otherwise scarce or unique in their composition. If a moderate nucleus can create such a statistically significant stream, what then might be the consequences of a truly massive one? This brings us to the third and most provocative tier of our analysis, a contemplation of scale that pushes the boundaries of the plausible into the realm of the transformative. Let us entertain, for a moment, the possibility that 3I divided by Atlas is not a mere pebble, but but the tip of a much larger, darker, and unseen structure, a monstrous nucleus. Far exceeding the conservative Hubble estimates, lurking within an unusually opaque or non-reflective coma, the outgassing and dust production from such a behemoth would be of a different order of magnitude entirely. The resulting debris field would not be a tenuous shower, but a veritable storm. The influx of micro-meteoroids into the Martian atmosphere would be so intense, so concentrated in time, that the ablation of these particles would deposit a significant, transient layer of metal ions, sodium, magnesium, iron, calcium, into the ionosphere. Our own Earth displays such layers, known as sporadic layers, but on Mars, with its tenuous atmosphere and lack of a global magnetic field, the signature of such an event would be stark and unambiguous: a brief, brilliant, and anomalous spike in the atmospheric chemistry, detectable by orbiting spectrometers. The boldest hypothesis thus emerges: a sufficiently large and active interstellar interloper is capable of imposing a short-lived but dramatic chemical signature upon the upper atmosphere of a terrestrial planet, effectively painting the sky with the elemental constituents of its own dust. Could the passage of a single visitor from the depths of space temporarily rewrite the chemical textbook of an entire world? The implications of this granular interaction transform Mars from a distant, rust-colored orb into a unique and fortuitous natural laboratory. If the dust density from 3I divided by Atlas is indeed as substantial as these escalating hypotheses suggest, then the red planet becomes a colossal sensor, its atmosphere a vast reaction chamber for studying the transport and integration of fine particles within an interplanetary, and indeed an interstellar, medium. Orbiting assets like the MAVEN spacecraft and trace gas orbiters would have the unprecedented opportunity to observe, in real time, the delivery and subsequent evolution of exotic materials into a planetary environment. The data returned would be invaluable for calibrating and refining our models of how microscopic dust grains, born in the cold nurseries around other stars, are transported, altered, and ultimately incorporated into the atmospheric and perhaps even surface processes of planets. This is not merely about observing a meteor shower, it is about understanding the very mechanics of material exchange on a galactic scale, using Mars as the experimental crucible and 3I divided by Atlas as the catalyst. What secrets of galactic material transport could be unlocked by observing the fallout from this chance encounter? Yet, as we ponder the physical footprint of this visitor, its mass, and the dust it sheds, a more profound mystery begins to surface, one that lies not in the quantity of the material being released, but in its fundamental quality, for the dust itself is merely the carrier, the visible manifestation of a deeper, more cryptic truth hidden within the chemical soul of the comet itself. The shadow it casts is long, but the light it absorbs and re-emits tells a story far stranger, a narrative written not in dust, but in the anomalous ratios of simple molecules, hinting at a formation history so alien that it challenges our very definition of a comet. And so we are compelled to look closer, to peer beyond the veil of dust, and into the spectral signature of its outgassing, where the James Webb Space Telescope has revealed a composition that defies all expectation, a chemistry where one compound reigns with a surprising and overwhelming dominance. It is a truth universally acknowledged, a paradigm etched into the very methodology of cometary science, that these icy wanderers are, at their core, fundamentally snowy dirt balls. Their identity is inextricably linked to the outgassing of water ice, the primordial steam of the solar system's birth, as it sublimates under the gentle caress of solar radiation, blossoming into the magnificent, incandescent coma that has captivated humanity for millennia. Yet, the object designated 3I divided by Atlas, this silent and enigmatic traveller from the interstellar void, appears to defy this foundational principle with a quiet, chemical obstinacy. Data streams from the most advanced eyes humanity has turned to the heavens, The James Webb Space Telescope and its near-spec instrument on that pivotal day of the 6th of August 2025 tell a story not of a water-dominated spectacle, but of a different exhalation altogether. The spectral fingerprints are unmistakable. The presence of H2O, both as ice and gas, is confirmed, yet it is the stark, dominant signature of carbon dioxide that commands attention, with a CO2 divided by H2O ratio standing among the highest ever recorded in the annals of cometary observation. It is as if we are witnessing not a comet, but a chemical paradox, a body that breathes not the familiar mist of water, but the dry ice of a different, colder genesis. Could it be that our most fundamental assumptions about the composition of interstellar nomads are merely a reflection of our own, parochial solar system's conditions? According to current models, a comet's composition is a frozen ledger, a direct record of the temperature and chemical conditions of its protoplanetary disk at the moment of its formation. A preponderance of CO2 over H2O could simply indicate an origin in the profoundly cold outer regions of its blazing home system, a place where carbon dioxide could condense more readily onto dust grains than water itself, creating a core richer in this volatile compound. This would be a fascinating data point in itself, a clue to the thermodynamic architecture of a star system we will never directly visit. Scientists suggest this could be due to a formation zone far beyond the so-called CO2 snowline, a distant and frigid frontier where such chemistry is not just possible, but expected. The initial, mainstream interpretation is one of a thermodynamic quirk, a simple matter of where, not what, this object was born from. But that doesn't account for the sheer intensity of the outgassing, the vigorous and seemingly lopsided eruption of CO2 that appears to be the primary engine of 3I divided by Atlas's minimal activity. If its water is largely locked away, what mysterious internal heat source, or what unique porous structure, preferentially liberates the carbon dioxide with such efficiency, leaving the water ice as a mere spectator to this anomalous exhalation? This leads us to the first, more speculative layer of hypothesis. The dominant CO2 jet, relentlessly venting into the vacuum and mingling with the fine cometary dust, may be generating more than just a visible coma. It could be creating a transient, localized chemical weather system. As this cold, dense stream of gas and particulate matter intersects the tenuous upper atmosphere of Mars, it does not simply disperse. It imposes a temporary exotic microclimate. The initial analysis posits a level 1 effect. This injection of exogenous CO2 subtly alters the local radiative balance at high altitudes. Carbon dioxide, a potent greenhouse gas in thicker atmospheres, behaves differently in the razor-thin air of the Martian thermosphere. Here, its presence can modify the rates of radiative cooling, creating a faint, localized thermal anomaly, a cool spot in the atmospheric fabric, a ghostly imprint of the comet's passage. It is a minor perturbation, a whisper of thermodynamic change, but in the exquisitely balanced systems of a planetary atmosphere, even a whisper can have an echo. What other, more dynamic interactions might arise when a stream of foreign gas meets a planetary boundary layer charged with solar energy? The narrative deepens considerably when we introduce the catalyst of dust. The CO2 outflow is not pure, it is a carrier, a river of gas ferrying innumerable microscopic particles of cometary material. This mixture provides the foundation for a level 2 hypothesis, one that ventures into the realm of plasma and charged particles. As this dusty CO2 plume is injected into the Martian high atmosphere, it is bathed in the relentless stream of the solar wind and bathed in intense ultraviolet radiation. The dust grains, acting as vast surfaces relative to atoms, become charged, while the CO2 molecules are readily ionized. This creates a temporary and highly unusual ion chemical environment. We are no longer speaking of simple gas dynamics, but of a reactive plasma soup, CO2 ions, electrons, and charged dust particles interacting in ways not commonly seen in the Martian environment. This is not the calm addition of a new gas, but the sparking of a temporary chemical furnace at the edge of space, a fleeting laboratory for reactions that could produce transient and exotic molecular ions. Could this anomalous plasma, this brief, dusty electrical storm, begin to influence not just the chemistry, but the very physics of Mars's magnetic frontier? To pursue this thread is to arrive at the most profound and speculative of the hypotheses, a level 3 conjecture that ties the comet's exotic breath directly to the planet's induced magnetosphere. Mars, lacking a global dipole magnetic field, possesses a complex magnetic environment generated by the interaction of the solar wind, with remnant magnetic fields locked in its crust. The boundary of this induced magnetosphere is a dynamic and porous interface. The proposed CO2 dust plasma, this splotch of anomalous chemistry, does not merely float passively. As a region of altered conductivity and charge density, it could act as a temporary and localized perturbation on a global scale. The hypothesis suggests that this CO2 plasma splotch might trigger a temporary reconfiguration of the ion escape flows at the very fringes of the Martian magnetosphere. It could open a temporary, enhanced channel for atmospheric ions to be stripped away by the solar wind, a short-lived but significant augmentation of the planet's perpetual slow bleed of its atmosphere. The comet's passage would thus inscribe its signature not merely in light and gas, but in the fundamental balance of planetary protection, a subtle rewiring of Mars's defensive shield for a brief, cosmic moment. If such a transient, yet profound, interaction is possible, what other, more subtle and potentially more hazardous, interactions might we have failed to anticipate in previous encounters? The consequence of this entire sequence of chemical and physical anomalies is, paradoxically, a magnificent opportunity. The Martian atmosphere, in this scenario, becomes a temporary canvas upon which 3I divided by Atlas paints its history. This AO2 fingerprint, this interstellar spore left upon the red planet's high atmosphere, provides a unique chance to trace not just the comet's immediate path, but its deepest origins. By analyzing the isotopic ratios of the carbon and oxygen within that deposited CO2, by studying the specific chemical byproducts of the plasma reactions, we could, in principle, decipher the environmental conditions of the molecular cloud or protoplanetary disk where this object was forged. Mars becomes a gigantic analytical instrument, its atmosphere a mass spectrometer, capturing a sample of true interstellar matter. This is not merely the study of a comet, it is the first tangible opportunity to conduct a detailed chemical autopsy on a visitor from another star, to read the recipe of a world born in the light of a foreign Sunday. But as we stand poised to decode this chemical message, a more unsettling question begins to form, one that shifts the focus from scientific opportunity to potential peril. If the simple act of breathing a strange gas can so perturb a world, what greater disturbances might its passage unleash? The precedent for such concerns is etched not in speculation, but in recent solar system history. In the close passage of Comet C divided by 2013, a one-siding spring by Mars in 2014. That event, while resulting in no direct impact, demonstrated that the true danger of a near miss may not be collision, but contamination, a different kind of violence inflicted upon a planetary system. The Martian atmosphere was subjected to a profound, if temporary, meteor storm as the planet ploughed through the comet's debris trail. This event did more than just provide a celestial light show. It violently churned the upper atmosphere, injecting a significant mass of foreign metals and ions material from the heart of a comet directly into the ionosphere. The effects were transient on a human timescale, but they were deep and widespread, altering the atmospheric chemistry and electrical properties for a period. A stark reminder that a near miss can still be an intimate encounter. The scenario with Siding Spring was a natural experiment, a demonstration of a planet's vulnerability to the dusty wake of a passerby. So, if a native solar system comet could induce such a significant atmospheric disturbance, what then might be the consequences of a close encounter with an interstellar object, one with a fundamentally different and more vigorous outgassing profile? For 3, I divided by Atlas, the worst-case scenario, excluding a direct impact that is not in the realm of possibility, evolves from the Siding Spring precedent into something potentially more complex and electrically charged. It is not merely a storm of meteoric dust, but the conjuring of a hybrid transient phenomenon, a dust plasma storm. The comet's peculiar CO2-dominated outgassing, laden with fine particulate matter, would provide the raw material. Its interaction with the solar wind and the Martian upper atmosphere, as previously hypothesized, provides the energy and the mechanism. The result could be a short-lived but intense perturbation of the planet's ionosphere, the electrically charged layer of the atmosphere critical for radio communication, and crucially, a protective buffer for the surface. This would not be a simple meteor shower, it would be an atmospheric electrical event, a scrambling of the planet's natural electromagnetic signature. The direct and most immediate concern would be for the fleet of robotic orbiters, the eyes, ears, and data relays for our entire Martian enterprise. These sophisticated machines, from NASA's MAVEN to the ESA's Trace Gas Orbiter, could be subjected to unexpected electrostatic discharges, heightened atmospheric drag from the injected material, and severe interference with their communication and sensing instruments. A sufficiently powerful ionospheric disturbance could effectively blind and deafen our robotic emissaries for a critical period, isolating the surface assets from their lifeline to Earth. The question then becomes not one of planetary destruction, but of technological vulnerability. The greatest risk may not be to Mars itself, but to our fragile, electronic presence upon and around it. As we contemplate the silent, chemical breath of this interstellar wanderer and its potential to stir the electric winds of Mars, we are forced to ask, are we, in our quest to understand the cosmos, merely spectators, or have we become a part of the planetary system we observe, and thus vulnerable to its most subtle and distant interactions? Of all the celestial hazards that a world might face, the most cinematic is undoubtedly the cataclysm of direct impact, a titanic collision that reshapes landscapes in an instant of apocalyptic fire. Yet, for a world like Mars, a planet already stripped of its protective mantle of air and the comforting embrace of a global magnetic field, there exists a more subtle, more insidious threat. It is a danger that does not require the violence of a direct hit, a peril that whispers rather than roars. The comet's nucleus, a frozen mountain of ice and dust, could pass at a safe remove, a mere spectacle in the Martian sky, and yet its most profound legacy would be written not in craters, but in the planet's tenuous upper atmosphere. It would not be a hammer blow, but a breath laden with fine, cosmic dust. This is the true, understated menace, the transformation of Mars into a vast, resonating plasma wind chime, its ionosphere set ringing by the gentlest of touches from the void. According to current models of cometary composition and behavior, the coma and the immense tail streaming from a comet like Comet Siding Spring are essentially a diffuse cloud of fine particulate matter, ice crystals, and charged particles, a fog of primordial solar system debris. As Mars passes through this ethereal shroud, these particles, some no larger than grains of tobacco smoke, would enter the Martian atmosphere at hypersonic velocities. Each microscopic grain, upon collision with the sparse atoms of the upper atmosphere, would instantaneously vaporize into a transient, incandescent puff of plasma, a shower of 1 billion tiny meteors, none large enough to reach the surface, but collectively depositing a staggering amount of energy and exotic materials into the ionosphere. Scientists suggest this could be due to a simple, if dramatic, transfer of kinetic energy, a frictional heating so intense it disassembles matter into its constituent ions and electrons, momentarily and locally altering the atmospheric chemistry. But does this conventional explanation of ablative vaporization fully account for the potential for systemic chaos? The precedent was set, not in theory, but in observed reality. In October of 2014, Comet Siding Spring, C, divided by 2013, a 1, performed an exceptionally close flyby of the red planet, its coma gracefully enveloping the entire world. For a few fleeting hours, Mars was subjected to a meteor storm of unparalleled ferocity, a downpour of cometary dust that injected tons of foreign material, strange metals and ions like magnesium, iron, and sodium directly into its upper atmospheric layers. Research from the event confirmed the effects were both powerful and transient, a violent but short-lived perturbation. The planet's ionosphere, normally a placid layer of charged particles, was seared with intense, ultraviolet emission lines from these alien elements, a spectral signature of a global atmospheric wound that, while it healed, left a permanent mark on our understanding. The event proved that a comet's dust, its most ephemeral component, can indeed ring a planet. But what if the next comet carries a denser cloud of dust or a different compositional profile? Could a mere whisper of dust, a seemingly innocuous event, trigger a cascade of failure within the delicate technological ecosystem we have established in orbit? The initial consequence, the first and most benign level of this cascade, would manifest as a subtle corruption of the electromagnetic environment. The sudden, widespread infusion of vaporized metals and the resulting plasma turbulence would create a faint, planet-wide static, a gentle hiss across a wide spectrum of radio frequencies. This would not be a deafening roar, but a pervasive increase in the background plasma noise, a soft veil drawn over the precise measurements upon which our orbiters rely. The delicate instruments designed to listen to the solar wind, to map the weak magnetic anomalies of the crust, or to study the natural plasma waves of the magnetosheath, would find their data adulterated by this artificial, cosmic interference. Their readings would become ambiguous, their clean signals now laced with the ghostly imprint of the comet's passage. Could we even trust the data collected during such an event, or would it all be relegated to the archives as corrupted, anomalous, and ultimately useless? Yet, the disturbance would not remain a mere matter of noisy data. The second, more profound level of this cascade would involve a fundamental distortion of the fields themselves. The injected plasma, a soup of ions and electrons with its own dynamic properties, would interact with and temporarily modify the local electromagnetic environment. Probes attempting to make precise measurements of Martian magnetic or electric fields might find their readings skewed, their phases shifted, as if the very fabric of space around the planet had developed a subtle warp. This would not be a mere inconvenience. For a spacecraft, its understanding of its orientation and its environment is paramount. Anomalous field readings, misinterpreted by sensitive onboard computers, could be perceived as a loss of attitude control, an unexpected tumble, or a proximity to a hazardous region. The most cautious of these artificial minds, programmed for self-preservation above all else, might therefore trigger their safe modes, shutting down non-essential systems and halting scientific operations until ground control could diagnose a problem that, in reality, was external to the spacecraft itself. Is the spacecraft's instinct for self-preservation, its greatest strength, also its greatest vulnerability in the face of an environmental phantom? This leads us to the precipice of the worst-case scenario, the third and most critical level of the cascade, a synchronized, systemic failure. Imagine not one, but a constellation of our robotic sentinels, MAVEN, the Mars Reconnaissance Orbiter, the Trace Gas Orbiter, and others simultaneously experiencing these phantom anomalies. A chorus of alarms, silent in the vacuum of space, would be registered in their core programming. One by one, or perhaps in a terrifying wave, their primary science payloads would autonomously power down, switching to protective configurations to shield their delicate optics and sensors from a perceived threat that is, in fact, the very atmosphere they are designed to study. For a few critical hours, the golden hours immediately following the comet's closest approach, when the most valuable data on atmospheric response and cometary interaction could be gathered, the entire orbital infrastructure around Mars would fall silent. The flow of data would cease, replaced by a stream of engineering telemetry reporting a fleet-wide retreat into safe havens. We would be blind at the moment of greatest spectacle, our eyes averted by their own automated reflexes. What profound secrets of planetary atmospherics and cometary science would be lost in that collective, protective blink? And yet, within this frustrating silence, within this orchestrated failure of observation, lies a perverse and unique opportunity. This worst-case scenario, this stress-induced coma of the orbital fleet, is in itself a priceless experiment. It is a spontaneous, unplanned, and utterly realistic stress test of the entire operational paradigm of robotic exploration at another world. We would be granted a brutal audit of the resilience of our spacecraft, the robustness of their fault protection algorithms, and the agility of our ground-based mission control teams in responding to a simultaneous, multi-spacecraft emergency. The recovery process, the slow and meticulous reactivation of each instrument, the forensic analysis of the sensor data leading up to the safe mode events, all of it would constitute a masterclass in spacecraft survivability. The comet's dust, therefore, would not merely be an agent of chaos, but also a merciless instructor, revealing the hidden fragilities in our interplanetary presence. So, we are left to ponder. In our quest to build machines resilient enough to brave the alien environment of Mars, have we perhaps failed to anticipate an environment that can become, for a few fleeting hours, profoundly and deceptively alien? For the answer, we must look back to a time when one of our sentinels did not look away, but stared directly into the storm. What did it see when the sky itself turned to metal? The Martian night, a vast and silent expanse, is a canvas painted with the faint, residual glow of a sun that has long since vanished beyond the horizon. Here, the tenuous atmosphere, a mere whisper of what it once was, holds secrets that are written not in light, but in the subtle language of atoms and ions. It was in this ethereal realm, high above the rusted plains, that the Maven spacecraft, a silent sentinel dedicated to understanding the soul of this world, witnessed a most peculiar phenomenon, a gentle, otherworldly rain, not of water, but of metal. The progenitor of this celestial metallurgy was none other than Comet Siding Spring, a visitor from the outermost dark, which in 2014 ventured perilously close to the red planet. As it passed, its immense coma, a shroud of vapor and dust, brushed against the upper reaches of the Martian atmosphere. Could it be that the enigmatic 3I divided by Atlas, a wanderer from the interstellar void, possesses the potential to enact a similar, perhaps even more profound, spectacle? If its own cometary heart were rich enough in metallic dust, might it too seed the Martian sky with an ephemeral glittering shroud, repeating that brief, anomalous night of 2014 for any future observer, robotic or human, to behold? The initial evidence for this metallic infusion was captured by Maven's Imaging Ultraviolet Spectrograph, IUVS, an instrument designed to read the ultraviolet signatures of a dying atmosphere. In the wake of Siding Spring's passage, the sensor detected fleeting, yet unmistakable, emission lines. The spectral fingerprints of magnesium and iron, both in their neutral and ionized states, tracing a temporary shimmering veil across the thermosphere. According to current models of cometary composition and atmospheric interaction, this was precisely the expected outcome. The minute dust particles, or meteoroids, shed by the comet would have encountered the thin Martian air at hypersonic velocities, ablating in a flash of frictional heat and sowing their constituent atoms into the high-altitude winds. The process is a well-documented, if dramatic, form of cosmic enrichment, a transient gift of heavy elements from a frozen wanderer. But does the simple fact of ablation and emission fully capture the deeper, more systemic implications of this event? For the signature was not merely one of light, but of lasting change, a transformation that would ripple through the very electrical fabric of the planet's atmospheric envelope. This leads us to the second, more profound level of analysis, revealed not by the eye of the spectrograph, but by the sensitive nose of the neutral gas and ion mass spectrometer, NGIMS. This instrument documented the brief but definitive formation of a distinct, the short-lived layer of metal ions, a transient ionosphere of iron and magnesium, nestled within the pre-existing structure of the upper atmosphere. Scientists suggest this could be due to the rapid photoionization of the ablated neutral atoms by the relentless barrage of solar ultraviolet radiation, creating a thin, electrically conductive stratum where none existed before. This layer, this sudden stratum of metallic ions, would have locally and significantly altered the electrical conductivity across a vast region of the Martian sky, creating a novel pathway for currents that flow from the solar wind into the planet's ionospheric shell. Yet, one must ponder, to what end does this temporary, metallic veil serve? Is it merely a passive, electrically active shroud, or does it initiate a more fundamental reorganization of the atmospheric system itself? We are thus compelled to venture to the third and most speculative tier of this hypothesis, a potential restructuring of the thermal and electron cycles within the critical altitude band of 120 to 200 kilometers. The introduction of a dense, new population of heavy metal ions, with their uniquely efficient radiative cooling properties and their role as potent electron sinks, could have initiated a cascade of feedback. The local electron temperature may have been suppressed, the thermal balance of the entire thermosphere subtly perturbed, and the sharp boundaries that typically define the ionosphere's layers may have been softened, blurred into a more diffuse and electrically complex interface. This would represent not a mere additive phenomenon, but a transformative one, where the cometary dust acts as a catalyst, temporarily rewriting the local rules of atmospheric physics. So, if a single, passing comet like Siding Spring could impose such a complex, multi-layered signature upon the atmosphere, what enduring mark might a more substantial, or more chemically peculiar, interloper, like 3I divided by Atlas, leave upon its canvas? Could the very history of atmospheric loss, etched into the isotopic ratios and the elemental gradients of the upper air, be partially decoded by reading the ephemeral scripts of these metallic rains? The opportunity presented by such high-altitude metallurgy is profound, for it offers a unique key to unlocking the deep history of the Martian atmosphere's demise. Each event of this nature is a controlled experiment, a punctual injection of known elements into the atmospheric engine, allowing us to trace their fate with exquisite precision. Do these heavy ions, dragged by planetary rotation and atmospheric tides, reveal the hidden circulation patterns of the upper atmosphere? As they are slowly transported downwards, do they serve as tracers for the global, relentless flow of gases that are ultimately stripped away by the solar wind? The presence of these metals is a chronometer and a flow meter, a way to witness the processes of escape in near real time. Observing the dispersal and eventual disappearance of such layers provides a direct measurement of the rates and pathways of atmospheric loss, painting a dynamic picture of a world slowly bleeding its air into space. But if metal ions can so effectively trace the atmosphere's final journey, what of the more complex solid remnants of these cosmic visitors, the smoke that remains after the metallic fire? What role might these minute, lingering particles play in the ongoing atmospheric drama, perhaps even seeding new and unexpected forms in the thin, cold air. For it is in the wake of this evaporative rain that another, more subtle process begins. The immense heat of ablation does not merely release atoms, it also forges, through a process of recondensation and nucleation, a population of minuscule, solid particles known as meteoric smoke. These nanoscale fragments, the residual cinders of vaporized dust, drift languidly through the upper atmospheric layers, invisible to all but the most indirect of detection methods. On Earth, this cosmic soot is known to serve as the fundamental nucleation sites for the formation of enigmatic noctilucent, or night-shining, clouds that glow with an electric blue in the polar summer mesosphere. It is a chain of logic, inferred from planetary comparison, that suggests a parallel possibility for the red planet. Could these same particles, these seeds of celestial origin, be the hidden architects behind the formation of high, wispy, and peculiarly tenuous clouds that have been glimpsed in the Martian twilight? The conditions are certainly ripe. A cold trap exists in the mesosphere, and the atmosphere, though thin, possesses carbon dioxide and trace water vapor capable of depositing upon a suitable surface. And here, the unique nature of an object, like 3i divided by Atlas, invites a deeper curiosity. Should its composition prove to be as extraordinary as its origin, perhaps rich in volatile ices like carbon dioxide, far beyond the typical profile of a solar system comet, the resulting meteoric smoke could possess a fundamentally different chemical character. This exotic smoke would then act not as a generic nucleus, but as a specialized one, potentially triggering the condensation of CO2 ice crystals in altitudes and conditions where they are otherwise unforeseen. The resulting cloud forms would be spectral and strange, leaving an atmospheric fingerprint entirely unique to this interstellar visitor. They would be clouds born not of the planet's own cycles, but of the chemistry of a distant star, a ghostly, nocturnal bloom seeded from the void. Is it possible, then, that the most lasting monument to a comet's passage is not the brief, brilliant streak of a meteor, but the slow, silent genesis of a cloud, a transient, shining monument woven from the very fabric of the cosmos? Consider, for a moment, the twilight sky of Mars, a vast and tenuous canvas brushed with the last cold light of a distant Sunday. Here, in the profound chill of the upper atmosphere, a spectacle unfolds that is both ethereal and enigmatic, the appearance of the noctilucent or night-shining clouds. These are not the water ice clouds of Earth, but rather spectral formations of carbon dioxide ice, clinging to existence in the thin Martian air, glowing with a faint, silvery luminescence long after the sun has dipped below the horizon. According to current atmospheric models, their genesis requires a catalyst, a minute solid particle upon which the sparse carbon dioxide molecules can condense and assemble into a visible structure. The conventional explanation points to the constant, gentle rain of cosmic dust, the microscopic debris left in the wake of comets and asteroids, which perpetually seeds the Martian skies with potential nucleation sites. This meteoric smoke, as it is known, is a well-documented phenomenon, a fundamental ingredient in the high-altitude chemistry of worlds across our solar system. But what if, on occasion, this gentle rain becomes a sudden, concentrated downpour, seeding not just clouds, but a cascade of atmospheric anomalies that whisper of processes far more complex and far-reaching than we have ever imagined? The hypothesis emerges from the passage of a wanderer, the comet C divided by 2013, a one-siding spring, which in 2014 grazed the Martian atmosphere, inundating it with a uniquely dense and exotic stream of cometary dust. This event, a celestial experiment conducted on a planetary scale, provided a fleeting glimpse into a possible mechanism that such a concentrated influx of interstellar material, this Coithian Thatch, or meteoric smoke, could act as a potent trigger for anomalous nocturnal cloud formations on the red planet. The data gathered in the wake of Siding Spring revealed a temporary but dramatic alteration of the upper atmospheric layers, with models suggesting a prolific injection of fine dust particles. Could it be that the spectral signature of these noctilucent clouds, particularly the subtle absorption lines of solid CO2, is not merely a testament to the cold, but also an imprint, a ghostly signature, of the foreign nuclei around which they formed? Is the very light they reflect and absorb telling a story not just of Martian climate, but of its interaction with the dust of a distant comet? The evidence for this mechanism, while indirect, is compellingly rooted in the extrapolation of established science. The concept of meteoric smoke particles acting as condensation nuclei is a cornerstone of astronomy, the study of planetary upper atmospheres. Following the Siding Spring event, observations from orbiting spacecraft detected a significant and abrupt increase in high-altitude metal ions, the vaporized remnants of infalling dust, confirming that the comet had indeed delivered a substantial payload of particulate matter into the Martian system. Computational models simulating the aftermath showed a sharp spike in the density of potential nucleation sites, creating conditions ripe for the rapid formation of high-altitude ice clouds. The stage was set, the ingredients measured. The theoretical framework for this celestial seeding was firmly established by a real and observed interplanetary event. Yet, does the confirmation of the mechanism's possibility necessarily bound the extent of its consequences, or did we merely witness the opening act of a far more intricate atmospheric drama? Our analysis begins at the first, most subtle level of this phenomenon, the appearance of a thin, silvery veil at the edge of night, a noctilucent cloud layer manifesting as a faint, optical variation against the deepening twilight. These are tenuous structures, visible only through the most sensitive orbital images or under perfect observational conditions from the surface, their presence betrayed by a gentle, almost imperceptible, the brightening of the nocturnal sky. They represent the most benign interpretation of the hypothesis, a direct and expected outcome of an enhanced density of condensation nuclei. The meteoric smoke provides the canvas, and the condensing atmospheric CO2 provides the paint, resulting in a cloud that is beautiful, yet ostensibly straightforward. But can the serene appearance of a silvered cloud truly be divorced from the violent, high-velocity origins of the interplanetary dust that may have spawned it? The narrative deepens with the second level of anomaly, the emergence of irregular, high-altitude cloud bands, structures that defy the predictable patterns of atmospheric circulation. These are not uniform veils, but rather structured formations, streaks and filaments that exhibit unusual persistence and geometry. Their presence is registered not only in the visible spectrum, but through their interaction with other wavelengths. Data from orbital spectrometers reveal distinct and somewhat puzzling attenuation in specific ultraviolet and infrared channels as they pass through these formations. This suggests a cloud composition or particle size distribution that is anomalous, a deviation from the standard model of pure CO2 ice crystals. The mere presence of a nucleus is one thing, but the physical and chemical properties of that nucleus, its shape, its porosity, its spectral affinity could fundamentally alter the microphysics of the ice that forms upon it. Could these anomalous UV divided by IR signatures be the direct fingerprint of the exotic meteoric smoke particles themselves? Their unique properties orchestrating the formation of ice crystals in a way that native Martian dust never could? Then, we encounter the third and most profound level of this mystery, the sudden manifestation of a dense, localized curtain of high-altitude particulates, an event so abrupt and optically thick that it effectively scatters and absorbs a significant portion of the thermal infrared radiation emanating from the surface below. For the instruments aboard an orbiting spacecraft, This translates into a map of the Martian surface that inexplicably softens, its familiar features rendered blurred and indistinct for the duration of several orbits, before the obscuration dissipates as suddenly as it appeared. This is no mere cloud, it is an atmospheric occlusion. The conventional explanation might posit an unusually dense and localized burst of noctilucent cloud formation, perhaps fueled by a transient pocket of atmospheric updraft or a particularly concentrated filament of cometary dust. However, the speed of its formation and dissolution challenges our understanding of cloud dynamics at such rarefied altitudes. What force could choreograph the atmosphere to conjure and then dismiss such a substantial veil with such swiftness? Does this event represent the upper limit of cloud seeding, or does it point toward a more dynamic and energetic interaction between the incoming dust and the Martian atmosphere itself, an interaction that transcends simple condensation and ventures into the realm of plasma and charge? The implications of capturing and analyzing these very condensation nuclei, these seeds of interstellar origin, would be a watershed moment in planetary science. It would mark the first time humanity could directly observe how extrinsic matter, born in the frigid outskirts of a distant stellar nursery, or in the eruptive death throes of a comet, actively intervenes in the meteorological cycle of another world. We would move from inference to inspection, holding in our data the very agents of change. We would learn not only about the composition of the cosmos, but about how that composition sculpts the atmospheres of the planets it encounters. This is the grand opportunity, to witness, in real time, the galaxy imposing its will upon a local environment. But if these microscopic seeds can so profoundly influence the visible structures of our skies, what other, more invisible influences might they be exerting upon the very fabric of the Martian atmosphere, upon the delicate balance of its constituent gases? Could the gentle fall of dust be the prelude to a far greater, more fundamental loss? For the same influx of fine particulate matter that seeds the clouds does not simply vanish, it settles, it ablates, it ionizes, becoming a permanent, if diffuse, component of the upper atmospheric layer. And in doing so, it may be initiating a chain of consequences that reaches into the ionosphere, altering its electrical properties and potentially opening a temporary, yet measurable, channel for the atmosphere to bleed away into the void. The delicate dance of energy and particles in this region is governed by complex electrodynamics, and the introduction of a massive, sudden source of charged dust could disrupt this balance in profound ways. The anomalous clouds, therefore, may be but the visible, serene echo of a far more violent and consequential process unfolding in the thin, charged air above them. What begins as a seed for a beautiful night-shining cloud might ultimately become a key, however temporary, that unlocks a door through which the soul of the atmosphere itself begins to escape. The Martian atmosphere, a tenuous veil of carbon dioxide clinging to a world that has known better days, is a chronicle of loss. It is a story written in the faint pressures, measured by landers, and the isotopic ratios locked within ancient meteorites, a narrative of a world that once boasted a thicker, warmer envelope, capable of sustaining liquid water and, perhaps, the nascent whispers of life. This grand exodus of air, playing out over billions of years, is often portrayed as a slow, inexorable bleed, a gradual stripping away by the solar wind under a weakening magnetic field. Yet, what if this process is not always so gradual? What if the void between the planets, far from being empty, occasionally delivers a catalyst that can momentarily pry open the atmospheric valves, accelerating this loss in a fleeting, violent sigh? The passage of a sizable comet, such as C, divided by 2023, A1 Tsuchinshan Atlas, through the Martian system, presents a natural experiment of precisely such a phenomenon, a chance to witness atmospheric escape not as a geological statistic, but as a dynamic real-time event. When the dust and ionized gas of a comet's magnificent tail begin to pour into the upper reaches of the Martian atmosphere. The delicate equilibrium of this high-altitude frontier is profoundly disrupted. According to current models, the influx of cometary material, particularly the fine dust particles, acts as a form of high-altitude ablation. These myriad microscopic projectiles, vaporizing upon entry, deposit their kinetic energy directly into the thin air, seeding it with metallic ions and creating a transient, artificial layer of ionization. Simultaneously, the solar wind, already sculpting the Martian magnetosphere, is further perturbed by the comet's own complex plasma environment, potentially compressing the planetary boundary and driving enhanced interaction. Mainstream scientific explanation suggests this could lead to a short-term measurable increase in atmospheric escape rates, a phenomenon glimpsed in the aftermath of comet Siding Spring's close pass by Mars in 2014. The Standard Model posits that this is a straightforward, if dramatic, case of energy transfer and subsequent atmospheric heating. But does this conventional energy deposition model fully account for the unique, multifaceted assault of a comet, which delivers not just energy, but also foreign matter and profound magnetic disturbances directly into the system's heart? The more speculative, and perhaps more compelling, hypothesis is that the 3I divided by Atlas stream induces a specific and potent form of electron heating, one that significantly increases the diffusion gradient within the ionosphere and, in turn, acts as a temporary pump for the accelerated loss of heavy ions like O2 mice and CO2 mice. While solar extreme ultraviolet radiation is the usual driver of ionization, the cometary influx provides a different, more chaotic energy spectrum. The cascading collisions and charge exchange processes between incoming cometary particles and atmospheric constituents could preferentially transfer energy to the electron population. These hot electrons, in their agitated state, would increase the scale height of the plasma, effectively reducing the gravitational binding energy for the heavier ions and facilitating their upward flow. It is not merely a case of the atmosphere being stirred, it is a fundamental, albeit temporary alteration of the thermodynamic and electrostatic conditions that govern the exospheric boundary. Could it be that a comet's most lasting impact on a planet is not a crater, but an invisible, thermodynamic lever, briefly pulled to release the very breath of a world? Post-event simulations and retrospective analyses following the passage of comet Siding Spring provided the first tangible data to move this concept from theory into the realm of observed phenomenon. Models run in the wake of that encounter indicated a short-term enhancement in ion loss, particularly of magnesium and iron ions sourced from the comet itself, but also a noticeable uptick in native planetary ions. Spacecraft like NASA's MAVEN Mars Atmosphere and Volatile Evolution mission, designed specifically to study atmospheric escape, detected a significant restructuring of the ionosphere and a sharp increase in the flux of escaping ions in the days following the comet's closest approach. This was not a prolonged event, but a sharp, distinct pulse, a spike on the otherwise steady graph of Martian atmospheric decline. The data suggested that such cometary interactions open a measurable, if ephemeral, channel for atmospheric loss. But if this channel was so clearly opened once, what are the cumulative effects of such events, repeated over the lifetime of the solar system? Has the sporadic visitation of comets been a silent, punctuated architect of planetary desiccation? The analysis of such an event unfolds across multiple tiers of consequence, each layer revealing a deeper integration of the transient cometary influence into the Martian system. At the most immediate and fundamental level, we witness a Level 1 analysis, a transient increase in the escape rate lasting for mere hours, leaving behind a distinct streak or signature in the ion composition of the exosphere. The enhanced loss does not affect all species equally. The specific chemistry and physics of the interaction, the resonance of charge exchange, and the mass-dependent nature of the diffusion process would impart a unique isotopic or molecular fingerprint to the escaping plume. This is not a uniform evaporation, but a selective filtration, where certain ions are preferentially ejected into the solar wind. What lasting chemical scar might such a violent, selective exhalation etch upon the upper atmosphere? Delving deeper, a Level 2 analysis reveals that this event fundamentally alters the structure of the E and F layers of the ionosphere. These regions, responsible for reflecting and refracting radio waves, would be rendered turbulent and unpredictable. The influx of cometary metals and the intense localized ionization create a tangled dynamic plasma environment. This would manifest as profound disruptions to radio communications and radar sounding between orbiters, landers, and Earth, turning the planet's ionospheric shell into a chaotic mirror. For a few critical hours, our technological probes would be navigating a planet suddenly gone radio dark, or filled with strange echoes and scintillations. What secrets of plasma physics and atmospheric turbulence are hidden within this temporary breakdown of our conventional means of perception? The most profound implication, a Level 3 analysis, posits that a sufficiently large pulse of atmospheric escape, as potentially triggered by 3I divided by Atlas, could be of a magnitude significant enough to be visible within the planet's seasonal evaporative budget. While the long-term climate of Mars is governed by Milankovitch-like cycles affecting the sublimation of the polar caps, a single, massive cometary-induced loss event could inject a step change, a non-linear jolt into this slow climatic rhythm. It would represent a loss of volatiles that would otherwise take years, perhaps decades, of steady solar-driven escape to achieve. This transforms the comet from a mere passerby into a potential agent of abrupt climate forcing, a geologic punctuation mark in the long sentence of Martian history. Is it possible that the climatic fate of a planet can be swayed not only by the slow dance of its orbit, but by the chance, violent embrace of a celestial wanderer? The consequence and opportunity here are profound. These temporary high-resolution signatures of atmospheric loss provide a unique calibration point for the long, blurred history of Martian atmospheric evolution. By measuring the precise magnitude and composition of a modern-day escape pulse, we can work backwards, refining our models of how such events, repeated over eons, have contributed to the planet's transition from a warm, wet world to the cold, arid desert we see today. Each ion lost during the 3I divided by Atlas encounter carries a story not just of its own ejection, but serves as a key to deciphering the cumulative loss of billions of years. The fleeting disturbance becomes a Rosetta Stone for the grand saga of planetary change. But to read this stone, to capture the subtle, rapid nuances of this atmospheric shudder, requires more than a fortunate alignment of celestial bodies. It demands a prepared and precise witness, a sentinel in the perfect position to record the event. This very preparation is now underway, a silent coordination in the void above the red planet, as the orbiters we have placed as guardians around Mars are being tasked to become active observers of this cosmic interaction. How will these robotic sentinels, poised in their silent orbits, capture the moment the comet's breath touches the atmosphere of Mars? When a visitor from the interstellar void makes its passage, every eye upon Mars must open wide. From the rust-red plains below to the robotic sentinels in the sky above, a singular, unprecedented command is issued: observe. This is not a mere astronomical event, it is a moment of cosmic communion, a fleeting handshake between our solar system and the vast, uncharted realms beyond. The hypothesis, as audacious as it is precise, posits that a synchronized campaign, a grand ballet of machinery named Hubble, James Webb, Mars Express, the Trace Gas Orbiter, and MAVEN, could capture the first true documentary of an interstellar comet's intimate encounter with a planetary atmosphere. For the first time, we would not be passive spectators of a distant light, but active chroniclers of an interaction, recording the very breath of a planet as it is stirred by a ghost from another star. The empirical foundation for this endeavour is already being laid in the meticulous logs of mission control. The European Space Agency has publicly charted the observing windows for its Martian fleet Mars Express and the Trace Gas Orbiter, their instruments poised and calibrated for the critical period of the 1st through the 7th of October. The moment of closest approach, a mere 30 million kilometers on the 3rd of that month, is not a threat but an invitation, a perfect proximity for detailed study. Simultaneously, across the vast gulf of space, NASA has deployed its most powerful eyes, the veteran Hubble Space Telescope, tasked with constraining the object's true dimensions and morphology, and the revolutionary James Webb Space Telescope, its infrared gaze poised to dissect the chemical soul of the comet's coma, to read the spectral lines that whisper of its alien origin. This is not a collection of disparate observations, but a premeditated, interagency symphony. The first level of analysis, therefore, is the acquisition of a simultaneous, multi-channel dataset, a sensory overload of the highest scientific order. We are speaking of a confluence of data streams, high-resolution imagery, capturing the dynamic evolution of the coma and tail, spectroscopic fingerprints, revealing the molecular composition of outgassing ices, and in situ plasma sensors on the Martian orbiters, detecting the subtle tremors in the solar wind, as the comet's own magnetosphere, if it possesses one, brushes against that of the red planet. According to current models, this tripartite approach should allow us to deconstruct the comet's activity state, its production rates of water, carbon monoxide, and other volatile species, and its interaction with the interplanetary medium. It is the scientific method applied on a grand, cosmic scale, a process of systematic data collection. But does the mere collection of data, however comprehensive, guarantee true understanding, or does it simply present us with a more complex and beautiful mystery? This leads us to the second, more profound level of inference, the construction of a time-space map of a planetary atmosphere's response to the comet's dusty trail. As the comet's effluvia, a mist of fine dust and charged particles, sweeps across Mars, the fleet of orbiters will act as a distributed network of seismometers for the Martian sky. MAVEN, a specialist in atmospheric evolution, will monitor for any minute stripping of upper atmospheric particles, any telltale shimmer of auroral activity induced not by the Sun, but by this interstellar interloper. The Trace Gas Orbiter will scrutinize the chemical makeup of the atmosphere for any transient exotic compounds deposited by the comet's passage. Scientists suggest this could reveal how external stimuli can perturb atmospheric chemistry on short, dramatic timescales. But that doesn't account for the possibility of a more fundamental interaction. Could the specific isotopic ratios found in this interstellar material, imprinted upon the Martian high atmosphere, act as a permanent, if faint, signature of this encounter, a cosmic tag that would endure for millennia? The ultimate ambition, the third and most consequential tier of this endeavour, is to establish a canonical template, a standard model, for all future interstellar flybys. This event is not an endpoint, but a beginning. The data protocols, the observational strategies, the cross-calibration of instruments across different agencies and orbits, all of this will coalesce into a playbook for the next Oumuamua, the next Borisov. It is the foundation of a new discipline, the real-time study of interstellar objects. The meticulous records from this campaign would become the Rosetta Stone, allowing us to compare and contrast this visitor with the next, to begin classifying them, to understand if they are mere outliers or representatives of a vast, hidden population of galactic nomads. Yet, if we succeed in creating this template, are we merely perfecting our method for observing the messengers, while remaining ignorant of the message itself? The consequence, the grand prize of this coordinated vigil, is the creation of the first true atlas of an interstellar impact upon a planet, not an impact of collision, but of influence. This would be a foundational document, a primary source of unparalleled value for the coming era of human travel to Mars. Future colonists, gazing up at the Martian night, would no longer see the stars as mere points of light, but as potential sources of both wonder and data. Their textbooks enriched by the direct record of how their new world reacts to a touch from the galactic wind. This atlas would detail not just the physics and chemistry, but the very context of our place in a galaxy that is far more dynamic and interconnected than we ever imagined. But can any atlas, no matter how detailed, truly prepare us for the profound psychological shift of knowing, with certainty, that our solar system is not an island, but a port in a constant, flowing stellar current? And as we contemplate this golden window of observation, this orchestrated effort to capture a whisper from the void, we must also consider the tangible, physical reality of the visitor's passage. For the very particles that carry its secrets also carry a latent, pervasive risk, not of catastrophic impact, but of 1,000 tiny, insidious abrasions. What unseen dangers might this ethereal trail of dust pose to the fragile eyes and ears we have positioned so perfectly to listen? In the profound and perpetual silence of the interplanetary void, where the absence of sound is oppressor, physical law, there exists a threat that moves with a whisper, a presence felt only in the catastrophic moment of its arrival. It is a realm where velocity transforms the most insignificant of objects into instruments of profound consequence. A solitary mote of dust, no larger than a single micron across, a fragment so minute it would rest unseen on a human hair, becomes, when accelerated to the velocities that govern travel between the worlds, a silent bullet. Its passage is unheralded by any sonic boom, for there is no medium to carry the sound, yet its impact carries the concentrated energy of a miniature sun, a transient, devastating fury delivered on a point too small to see. This is not the dramatic, planet-shattering asteroid of popular cinema, but a far more insidious and pervasive danger, the constant, stochastic rain of hypervelocity dust, a cosmic sandblasting that operates on a scale both microscopic and astronomical. According to current models of the interplanetary medium, these particles are the scattered remnants of cometary tails and asteroidal collisions, perpetually swept through the solar system by the solar wind and gravitational dynamics. Their distribution is sparse, a mere few particles per cubic kilometer, yet for a spacecraft traveling at kilometers per second, this tenuous mist represents a constant statistical certainty of impact. Scientists suggest this could be due to the simple, unforgiving mathematics of kinetic energy, where mass is multiplied by the square of velocity, meaning that even a minuscule grain, at orbital speeds, can possess the punch of a high-velocity rifle round. But that doesn't account for the peculiar, non-linear effects such a transfer of energy can have on the delicate and complex systems of a modern orbital observatory or a surface lander. It reduces a mission, costing billions, and representing the pinnacle of human engineering to a participant in a game of cosmic roulette, where the bullet is a speck of ancient stone and ice. The hypothesis, then, is as elegant as it is alarming. A stream of this dust, though thin, possesses sufficient collective energy to enact a slow, inexorable erosion of surfaces, to generate unpredictable electrostatic discharges, and to introduce transient noise into the most sensitive of optical and electronic systems. It is a form of weathering that operates not over geological epochs, but over mission lifetimes, a subtle degradation that can mask itself as routine instrument noise or minor system aging. The precedent for such concern is not merely theoretical, but was etched into the operational logs of our robotic Sentinels at Mars in the year 2014. As the comet Siding Spring made its exceptionally close pass by the red planet, the entire fleet of orbiters, NASA's MAVEN and Mars Reconnaissance Orbiter, the European Space Agency's Mars Express, underwent a meticulously calculated ballet of orbital adjustment and attitude alteration. Their primary objective was not to avoid a direct collision with the comet's nucleus, an event of astronomically low probability, but to shield their most vulnerable components from the intensified shower of cometary dust particles expected to be flung from Siding Spring's inner coma. For a critical window of time, these sophisticated machines turned their hardened backs to the incoming stream, protecting sensitive solar arrays, optical lenses, and instrument apertures. This was a tacit admission from the world's leading space agencies of the very real and present danger posed by what, to a casual observer, would seem to be nothing more than interstellar dirt. A first-order analysis of such an impact reveals a cascade of consequences, beginning with the most benign yet diagnostically critical. At its most fundamental level, a hypervelocity dust strike can manifest as a sudden, transient brightening of a single pixel on a CCD sensor, a hot pixel that appears and vanishes in an instant. This is not a flaw in play, the camera's manufacturing, but the literal flash of light generated as the particle vaporizes itself, and a microscopic crater of the sensor's surface upon impact, a miniature lightning strike in a vacuum. Simultaneously, the delicate electronics of communication systems, particularly the sensitive low-noise amplifiers linked to antennae, may register a momentary dip in their signal-to-noise ratio. A burst of static that whispers of a distant, violent conversion of kinetic energy into an electromagnetic pulse. It is a ghost in the machine, a fleeting signature of destruction that leaves no permanent scar, yet its occurrence is a data point in the slow statistical accumulation of risk. But if such an event is so transient, so easily dismissed as cosmic noise, does its true significance lie not in the momentary glitch, but in the cumulative erosion of certainty it represents? Escalating to a second tier of severity, the analysis must consider the phenomenon of local electrostatic discharge. When a dust particle vaporizes upon impact, it creates a localized plasma, a cloud of ionized gas that can facilitate a sudden and uncontrolled equalization of electrical potential across a spacecraft's surface or within its internal subsystems. This is not a massive power surge, but a sharp, localized spike that can flip a memory bit, confuse a logic gate, or force a scientific instrument into an unexpected state. The result is not catastrophic failure, but a nagging inconsistency that often requires a ground-commanded reset of the affected device, a temporary loss of data collection, and a drain on human resources as engineers on Earth diagnose an event that left no physical evidence. It is a phantom malfunction, a brief seizure in the nervous system of the probe, from which it can recover, but which leaves mission controllers with a lingering unease. How many such unexplained resets across the fleet of human spacecraft are, in fact, the unmarked graves of these microscopic, interstellar projectiles? The third and most profound level of this speculative analysis contemplates a more sustained and systemic assault, a microscopic sandblasting event. Imagine not a single impact, but a brief, concentrated passage through a localized cloud of this abrasive mist. The effect would be a cumulative one, not on electronics, but on the very surfaces that define the spacecraft's function and thermal balance. The delicate, mirror-finished surfaces of sunshields, critical for maintaining the cryogenic temperatures required by infrared telescopes like the James Webb, could be frosted with microscopic pits, degrading their reflectivity and thermal performance. Solar panels could suffer a measurable decrease in their power generation efficiency, as their light-capturing surfaces are subtly scarred. Optical navigation systems could see their lenses clouded by 1,000,000 infinitesimal scratches. The combined effect of such degradation could push multiple, independent systems to their operational limits, triggering a cascade of fault protections that would force the spacecraft into a safe mode for several orbits, suspending all science operations until the threat has passed and the vehicle's health can be fully reassessed from the ground. This would be a silent siege, where the enemy is not a software bug or a major component failure, but the slow, insidious accumulation of 1 trillion tiny wounds. Can a mission's longevity be ultimately determined not by its fuel or its funding, but by its resilience against this perpetual, invisible sandblasting from the depths of the galaxy? The consequence, and perhaps the opportunity, born from this pervasive risk, is a fundamental shift in how we design and operate our emissaries to other worlds. The encounter with Siding Spring and the growing awareness of the hypervelocity dust environment have actively spurred the development and refinement of data preservation, operational protocols for future surface missions, particularly those destined for environments like Mars, where dust is not only an interplanetary traveler, but a native feature, rich in abrasive CO2 ice and other minerals. These protocols are a form of cosmic conservatism, a philosophy that prioritizes the integrity of collected data over the continuous, uninterrupted operation of the platform. They mandate the regular, scheduled closing of sensitive instrument apertures during predicted dust storm seasons, the implementation of more robust shielding and grounding techniques to mitigate electrostatic discharge, and the design of redundant systems that can be cycled to distribute the wear and tear of this microscopic erosion. It is an acknowledgement that the greatest treasure these missions possess is the stream of data they beam back to Earth, and that protecting this stream sometimes requires turning the very instruments off, a paradoxical act of preservation through inactivity. But in this careful, cautious dance with an invisible adversary, are we merely treating the symptoms, while the greater, more fundamental question of the dust's ultimate origin and its role in the cosmic cycle remains shrouded in the darkness between the stars? And if this tenuous stream can so profoundly affect our machinery in the orbit of a single world, what greater, more systemic interactions might it be having on the planetary environment itself? Perhaps even weaving a connection between the vast, sun-driven bubble of the heliosphere and the thin, charged skin of a planet's ionosphere? For indeed, the journey of a dust grain does not end with its impact on a spacecraft. An ejection of material rich in CO2 and hydrogen cyanide, hurled from the Martian surface or from a passing comet, does not simply vanish into the void. It enters a dynamic and complex system of forces, beginning its interaction at the very frontier of a planet's sphere of influence. There, it meets the relentless flow of the solar wind, a supersonic stream of charged particles perpetually exhaled by the sunday. The collision, on a microscopic scale, is a violent one, stripping electrons from the neutral atoms and molecules within the dust cloud, creating a transient, localized plume of ionized plasma. This newly formed, diffuse cloud of charged particles then becomes entangled with the planet's magnetic and electric fields, however weak they may be. It is a phenomenon that would manifest not as a flash of light or a physical scar, but as a subtle, pervasive noise in the measurements of field and plasma instruments. Magnetometers would register faint, anomalous fluctuations. Langmuir probes would detect a shift in the local plasma density and temperature. For a few hours, or perhaps a few days, the fundamental geophysical readings of the planet would be skewed, rendered temporarily unreliable by this diffuse drifting fog of ionized matter. The data would show a planet in a state of quiet, anomalous agitation, a ghost signature of a distant, perhaps unobserved dust release. Could it be that our attempts to understand the intrinsic geophysical pulse of a world like Mars are continually, subtly, being influenced by these passing, invisible clouds of ionized dust, forcing us to question which signals are truly planetary, and which are merely the ephemeral scars of a cosmic weather that blows between the worlds? It is a presence felt before it is seen, a subtle disturbance in the silent, streaming river of the solar wind. 3. I divided by Atlas is not merely a speck of distant light in the eyepiece of a telescope. It is a stone cast into the placid plasma lake of our solar system, and the ripples it generates are propagating through the most fundamental medium of interplanetary space. As this interstellar wanderer, this enigmatic shard from a system unknown, continues its journey sunward, it exhales a breath of ancient volatiles, a coma rich in carbon dioxide and hydrogen cyanide, a composition confirmed by the unblinking eye of the James Webb Space Telescope, painting its portrait in the cold, precise light of the infrared. This gaseous shroud, when illuminated by the sun's relentless radiation, becomes a catalyst for a complex and invisible chain reaction, one that links the comet's own ephemeral atmosphere directly to the charged environment of Mars, forging a transient, ethereal bridge across the void. We are witnessing not a simple celestial passage, but the activation of a grand and intricate circuit, the heliosphere-ionosphere chain. According to current models of cometary physics, the intense solar heating of 3I, divided by Atlas's nucleus, was always predicted to trigger a vigorous outgassing, releasing trapped ices and dust into the vacuum. This cloud of gas and particulate matter, when swept by the supersonic flow of the solar wind, would naturally form an ionized coma and a tail that acts as a sort of conductive obstacle in the heliospheric flow. The precedent for such an interaction was meticulously documented when comet Siding Spring grazed the Martian system in 2014, its cometary material demonstrably causing a significant and rapid fluctuation in the planet's upper atmospheric chemistry and electron density, an event captured in detail by our orbiting sentinels. It is a known phenomenon, a predictable perturbation based on the established laws of plasma physics and atmospheric science. The upcoming observational campaigns planned by ESA and NASA for the window of October 1st to 7th are designed precisely to capture such an expected interaction, to measure the deflection of local magnetic and plasma fields around Mars with exquisite precision. But does the precedent of a local system comet truly prepare us for the intricate and potentially more profound disturbances wrought by an object forged in the crucible of another star? The initial analysis of the incoming data streams suggests a sequence of events that begins with a subtle, almost imperceptible tremor. At the first level of this cascade, our instruments register a series of oscillations in electron density, a gentle, rhythmic pulsing that manifests as a faint, coherent static whispering through particle detectors. It is the signature of the solar wind, that constant stream of charged particles beginning to entrain and accelerate ions from the comet's own effluents, creating a region of turbulent plasma that washes over Mars and its fleet of robotic observers. This is the expected signal, the initial confirmation of a physical connection being established across millions of kilometers. Yet, the very coherence of this signal, its patterned nature that seems to hold for longer durations than models would suggest, hints at a stability within the turbulence that is not easily explained by a simple cloud of disorganized gas. Could these rhythmic perturbations be merely the random noise of a plasma cloud, or do they contain within their patterns a more structured, and therefore more mysterious, form of organization? As the interaction intensifies, the narrative deepens, moving from a simple tremor to the formation of a distinct and transient structure. At the second level of inference, the data coalesces around the hypothesis of a plasma bubble, a localized region of exceptionally high ionization that forms briefly in the wake of the comet's influence. This bubble, a lens of altered space, possesses the capability to bend and delay radio signals, introducing a subtle but measurable lag into the critical communications with our deep space assets around Mars. It is a phenomenon that challenges the operational paradigms of interplanetary exploration, turning a clear channel into a murky one. The laws of electromagnetism provide a framework for understanding how a dense plasma can refract radio waves, yet the suddenness with which this bubble appears and the sharpness of its boundaries, as inferred from signal propagation delays, suggest a density and a definition that seem anomalous for a simple, diffuse cometary cloud. Is this a passive, chaotic structure, or could it be acting as a temporary and unintended lens, focusing and scattering our attempts to see and communicate with clarity? The third and most profound level of this analysis pushes our understanding into the realm of the truly consequential. The accumulating data from multiple platforms, orbiters measuring magnetic fields, landers monitoring sky brightness, and telescopes analyzing the comet's composition, begins to paint a picture not of a fleeting disturbance, but of a coherent, large-scale structure. We are forced to consider the possibility of a vast, crawling cloud of electric charge, a plasma phantom that slides along the orbital path of Mars, engulfing the planet in a short-term measurement storm. This is no longer a simple bubble, but an extended atmospheric entity, a temporary and artificial addition to the Martian space environment that creates havoc with any instrument designed to measure local fields and particles. It is as if a localized piece of the comet's own dynamic magnetosphere, a ghost of its interaction with its home star, has been transplanted momentarily into our own. This storm would not be of wind and dust, but of data and disruption, a cacophony of electromagnetic noise that obscures the true signal of the Martian environment. What fundamental processes, perhaps unique to the exotic chemistry of an interstellar object, could generate and sustain such a vast and organized plasma structure? And what might it tell us about the behavior of matter in the alien environments from which such visitors originate? The implications of this heliosphere-ionosphere chain are profound, transforming a celestial curiosity into an operational and scientific imperative. To understand this cascade from the solar wind's initial push to the ionization of the comet's volatiles, to the subsequent impact on the Martian ionosphere, is to grasp a fundamental key to safeguarding the future infrastructure of interplanetary civilization. Our satellites, our communication networks, and eventually our human explorers will all depend on a predictable and stable space environment. The passage of 3I divided by Atlas provides an unplanned, invaluable experiment, a stress test of our models, and a revelation of the hidden connections that bind all objects within a stellar system. It demonstrates that the space between planets is not an empty void, but a dynamic and interconnected medium, sensitive to the slightest touch from the world beyond. But if a single, small interstellar object can create such a palpable ripple in the fabric of our system, what might the passage of a larger one, or a swarm of them, do to the delicate technological web we are weaving around our world? And as we ponder the invisible electromagnetic storm, another, more tangible veil is beginning to descend, one that will challenge our ability to see the Martian surface itself. For the same cometary debris that seeds the plasma environment is also a cloud of fine exotic dust, poised to scatter and absorb the very light we use to probe the secrets of the red planet. The initial whispers from the spectrometers are subtle, a slight diminution of clarity in certain bands, a faint haze gathering at the edges of data. This is the prelude to the main event, the leading fringe of the cometary coma, now beginning its gentle, gravitational rain upon the Martian atmosphere. While the plasma physicists watch their signals dance and scatter, a different kind of obscurity is taking shape, one measured in photons and wavelengths. The fine, micron-sized dust particles, the ground-down remains of a world that never was, are now infiltrating the high atmospheric reaches of Mars. Their composition, alien and unweathered by our sun's particular light, introduces a new variable into the complex optical equations of planetary observation. According to the established principles of radiative transfer, this influx of exogenous particulates should act as an additive component to the Martian atmospheric aerosol load, increasing the scattering and absorption of light, particularly in the sensitive regions of the infrared and the ultraviolet. It is a predictable atmospheric optics problem, one for which we have extensive models developed from studying Martian dust storms and the high-altitude ice clouds that sometimes form. The scientific observation calendars for the critical months of October and November 2025 have long been drafted, filled with campaigns to map mineralogical distributions and to hunt for the elusive, biogenic signature of methane seepage. But can our terrestrial models, calibrated for native Martian dust, accurately account for the light-altering properties of dust forged in a completely different stellar nursery. The first and most direct consequence will be a measurable degradation in the signal-to-noise ratio, the fundamental metric of clarity for any remote sensing instrument. Observations conducted from orbit, such as those by the ESA's trace gas orbiter, will find their view softened. The sharp spectral features that betray the presence of specific minerals, olivine, pyroxene, hydrated sulfates, will begin to blur, their distinct peaks and valleys smoothed by the superimposed scattering signature of the cometary dust. This is more than a simple inconvenience. It is a loss of resolution, a fading of the hard-won details that allow us to read the geological history of Mars. The quest for methane, a gas that on Earth is a potent signature of life, is particularly vulnerable. Its detection relies on identifying exceedingly faint absorption lines in the near-infrared, lines that can be easily mimicked or obscured by the broad, smooth absorption and scattering effects of a diffuse aerosol haze. A negative result during this period would become scientifically ambiguous. Is there truly no methane, or is our window to the planet simply clouded? We are, therefore, presented with a difficult, real-time logistical puzzle, a need to recalibrate our expectations and redeploy our assets. The meticulously planned science campaigns must now be reassessed, their timelines potentially shifted to avoid this temporary, ethereal fog. But in this recalibration, are we merely avoiding a problem, or might we be missing a unique opportunity to study the atmospheric integration of exogenous material on a planetary scale? Yet, to view this only as an obscuration is to miss half of the story. The dust itself, while a veil to the surface, becomes a new object of intense study. The second-order effect of this influx is the creation of a novel, transient atmospheric layer, a stratospheric smear, of interstellar material. Spectrometers tuned to analyze the dust itself, rather than looking through it, will be presented with a pristine sample of another solar system. The scattering properties in the UV could reveal particle-size distributions alien to our own, while the infrared absorption features will write a chemical biography of the dust grains, their silicate, carbonaceous, or icy compositions, untainted by billions of years of residence in our own protoplanetary disk. This is a chance to perform, in situ, a form of interstellar geology to analyze the building blocks of a distant world without the need for a generations-long probe mission to another star. The fog is, in another light, the very subject we have longed to examine. So, do we fight the obscuration, or do we embrace it, turning our instruments away from the familiar red surface and towards the new, shimmering veil itself, to decipher the message it carries from the galactic dark? This leads to the most profound long-term implication. The gradual settling of this fine dust, a gentle snow of alien regolith, will leave a faint but permanent imprint on the surface of Mars. It will mix with the local soil, a subtle contaminant that future rovers and sample return missions may one day detect. It is a process that has likely been occurring for eons, as countless interstellar objects have passed through our system, each depositing a tiny fraction of its essence upon the planets. The passage of 3I divided by Atlas provides a rare, time-bound event to observe this process of cosmic deposition from start to finish. We can track the dust from its origin in the comet's coma, through its atmospheric suspension, to its final resting place upon the regolith. This completes a cycle of material transfer on a galactic scale, a direct delivery of extrasolar matter to a planetary surface within our own system. How many such layers of alien dust, each from a different interstellar visitor, lie preserved in the geological strata of Mars, and what might they tell us about the changing composition of the galactic neighborhood through which our sun has traveled? The temporary blurring of our view is a small price to pay for the chance to witness this ancient cosmic process in real time, forcing us to consider that the surfaces of worlds are not closed systems, but are, In fact, libraries collecting volumes of stellar history from across the galaxy. And as this dust settles, quietly marking the end of one phenomenon, it invites us to look further, to the next, and perhaps most unsettling question raised by this visitor. What if its most lasting impact is not on the environment of Mars, but on the very direction of our own future? It begins not with a cataclysm, but with a subtle dimming, a faint, ethereal veil drawn across the face of a world. The Martian surface, a landscape scrutinized by a fleet of robotic geologists and orbiting sentinels, has, for a moment, become slightly less knowable. The data streams, usually crisp and definitive, now carry a whisper of interference. A seemingly alien haze, a phenomenon requiring only a minute increase in particulate scattering, is sufficient to blur the precision of our mineralogical and atmospheric measurements. This is not the global dust storm of Martian legend, a titanic, native upheaval of rust-colored silt. This is something different, something exogenous, a faint breath of opacity exhaled from the depths of the void. Could it be that the very act of observation is being subtly filtered, our window onto the red planet clouded by an unseen hand? The mainstream explanation, of course, would seek a source within the known Martian environment. Planetary scientists would first turn to the complex dance of aerosols in the thin atmosphere. Perhaps it is a localized, high-altitude ice fog, composed of CO2, condensing in a peculiar thermal inversion. Current atmospheric models, refined by decades of data from orbiters like the Mars Reconnaissance Orbiter, could be invoked to simulate such an event, suggesting that transient microclimates at the poles or over the great volcanoes could generate a diffuse layer of scatterers. The instruments themselves, from the CRISM spectrometer on MRO to the sophisticated suites on the Trace Gas Orbiter, are calibrated for Martian conditions, but they are not infallible. Their algorithms for subtracting atmospheric effects are built on a library of expected phenomena. Yet, the timing of this obscuration is peculiar, its spectral signature anomalous. It does not perfectly match the scattering profile of pure water ice or CO2 clouds, and its onset appears correlated not with a shift in Martian seasons, but with the approach of a distant, silent traveler. This is where the speculative hypothesis unfolds, a narrative woven from the threads of celestial mechanics and exotic chemistry. The interstellar comet 3I divided by Atlas, a nomad from a star system beyond our own, is now plunging through the inner solar system. Its coma, that tenuous atmosphere of vaporizing ices, is expanding as it feels the sun's increasing warmth, and its dust tail is growing, a banner of primordial material streaming into the void. The James Webb Space Telescope, with its unparalleled near-spec instrument, has already confirmed the coma's rich composition, not just water, but significant amounts of carbon dioxide and carbon monoxide. The fictional leap, then, is to propose that this comet is not merely a passive spectator. It is shedding a fine mist of nanoparticles, a dust composed of water ice and solid CO2, a material that, upon being spalled into the interplanetary medium, could be swept by the solar wind into a vast, tenuous cloud. As this cloud intersects the orbital path of Mars, it could impose a temporary, faintly reflective filter upon the planet, a lens of alien dust that preferentially scatters and absorbs in the ultraviolet and infrared, the very wavelengths we use to probe mineral composition and trace gases from orbit. Could a celestial visitor, merely by its passage, drape a shroud of mystery over a neighboring world? The evidence for this exogenous scattering source is, in itself, a compelling astronomical record. The trajectory of 3I divided by Atlas is precisely known, its increasing activity meticulously documented. The European Space Agency has formally announced that its Mars Express and Trace Gas Orbiter missions will enter dedicated observation campaigns from the 1st to the 7th of October, 2025, a period calculated to be one of closest proximity and potential maximum effect. This is not a response to a Martian weather event, but a direct acknowledgement of the comet's potential influence. The comet's coma is a proven active source of dust and gas. The geometry of its approach places its debris field squarely in a position to interact with the Martian system. We are not imagining a phantom, but observing a known emitter of particulate matter on a collision course, in the broadest sense, with our field of view. What subtle transformations might occur when the pristine, complex chemistry of an interstellar object is introduced, even at parts per trillion, into the environment of a terrestrial planet? The analysis of this event unfolds across three escalating tiers of inference, each revealing a deeper layer of scientific consequence. At the first level, the effect is a matter of signal fidelity. The signal-to-noise ratio in specific UV and IR channels experiences a slight but statistically significant degradation. The high-resolution mineral maps, which usually render the surface in sharp compositional detail, begin to show a curious graininess, as if viewed through a sheet of frosted glass. The identity of individual clays, sulfates, and iron oxides becomes less certain, their spectral fingerprints blurred by the superimposed scattering signature of the exogenous aerosol. This is a nuisance for geologists, a temporary setback in the meticulous cartography of Mars, but it is a measurable, quantifiable nuisance. Is the truth of the Martian crust being momentarily lost in the statistical noise of an interstellar contamination? The second level of analysis delves into the more complex realm of atmospheric chemistry. The delicate measurements of trace gases, such as the enigmatic methane and the ever-present water vapor, begin to deviate from their established baselines. The algorithms on the trace gas orbiter, designed to peer through the Martian air and quantify its constituents, are now forced to contend with an additional, unaccounted-for scattering layer. A sudden apparent spike in methane concentration in a specific region could be an artifact, a phantom reading generated by the way the alien dust diffuses the light, passing through the true Martian atmosphere below. The very data we rely upon to answer profound questions about potential biological or geological activity becomes suspect, its integrity compromised by an external variable. How can we trust a whisper of biosignature when the medium through which we listen is itself humming an alien tune? The third and most profound level reveals the true cost of this celestial interference. For a few Martian orbits, the spectral window, itself the collective range of electromagnetic frequencies we use to observe the planet, becomes substantially clouded. Key observations, those high-priority surveys of ancient river deltas or searches for new gas plumes, are forced to be postponed. The science schedule, a meticulously planned document commanding the movements of billion-dollar assets, is thrown into disarray. The comet's veil, while thin, is pervasive enough to render certain types of investigation futile. We are not just losing data, we are losing time, the most precious commodity in exploration. The relentless march of scientific inquiry is forced to pause, not by a failure of our technology, but by the gentle, indifferent passage of a visitor from the stars. In our quest to master the observation of one world, have we failed to anticipate the subtle influences of another? The concluding hypothesis, therefore, frames this not as a catastrophe, but as a paradoxical opportunity. The short-term scientific risk is real. Data will be lost, campaigns delayed, and conclusions deferred. Yet, within this challenge lies a unique experiment. We are being presented, free of charge, with a natural laboratory for studying the effects of an exotic aerosol on remote sensing. The composition of 3I, divided by Atlas's dust, is a known variable, thanks to JWST. Its distribution and density can be modeled from its observed activity. By observing how this specific cloud corrupts our data, we can stress test our correction algorithms, refining them to be more robust, not just to Martian dust, but to any form of atmospheric interference. We are being forced to develop a more universal language of observation, one that can disentangle the signal of a planet from the noise of its cosmic environment. But if we can learn to see through this interstellar haze, what other, fainter veils might we then be able to pierce? This ephemeral shroud, however, is merely the most gentle of potential interactions. The comet's dust may cloud our vision, but its mass is negligible, a speck against the planetary bulk of Mars. The direct gravitational pull, calculated at a distance of 0.19 AU, is vanishingly small, a perturbation lost in the background noise of orbital mechanics from Phobos, Deimos, and the subtle tugs of the Sun and Jupiter. The true risk, the more profound influence, may not lie in force, but in form. It resides not in the comet's mass, but in its path, a geometry of intersection that turns a passive traveler into an active participant in the dynamics of the inner solar system. For 3I divided by Atlas travels on a path that is both familiar and alien, an orbit that brings its debris not just across our line of sight, but potentially across the very orbital plane of the planets themselves. Of all the forces that govern the celestial dance, gravity is the most familiar. The grand choreographer, whose invisible hand sculpts galaxies and binds planets to their stellar anchors. As the interstellar visitor designated 3I divided by Atlas began its precipitous dive into the heart of our solar system. The initial calculations provided a measure of comfort, its gravitational influence, a mere whisper against the monumental masses of the Sun and its planetary court, was deemed negligible, a force so slight it could be almost disregarded in the grand ledger of orbital mechanics. Yet, to focus solely on the magnitude of this pull is to miss the profound subtlety of the encounter entirely, for the true agents of consequence are not to be found in the strength of the pull, but in the exquisite, unyielding geometry of the path itself, the precise inclination of its orbital plane, and the subsequent orientation of its blossoming tail. The gravitational force may be the composer, but the geometry is the conductor, interpreting the silent score and directing the flow of cosmic material with a precision that pure force alone could never achieve. According to current models of solar system dynamics, a small, fast-moving body on a hyperbolic trajectory, such as 3I divided by Atlas, would exert a tidal force upon the planets so infinitesimal as to be lost in the noise of their own complex gravitational interactions. Its mass, estimated to be a mere fraction of even a small asteroid, places it firmly in the category of a celestial spectator rather than a gravitational player. The primary interaction, from a conventional standpoint, would be a brief, elegant, and ultimately inconsequential swing through the inner system, a data point for astronomers and a fleeting spectacle for telescopes, its passage notable only for its exotic origin. The European Space Agency's precise tracking data confirms this narrative of minimal gravitational disturbance, charting a path that, while bringing it within 0.19 astronomical units of Mars, does so without the slightest tremor in the Martian orbit, a testament to the robust stability of planetary motions over such short, violent timescales. The visitor, it would seem, is as ghostly in its gravitational signature as it is in its physical presence. But what if the true impact of such a visitor is not gravitational, but geometrical? What if the key lies not in the body itself, but in the wake it leaves behind? The speculative hypothesis emerges from the cold, hard facts of its trajectory. 3I divided by Atlas is not merely on a hyperbolic path, it is on a retrograde, highly inclined hyperbolic path. Cutting across the relatively flat plane of the ecliptic, the shared highway of the planets at a steep, slicing angle. This is not a gentle merge into traffic, but a violent intersection. As the comet's nucleus is warmed by the sun, it sheds a vast stream of dust and gas, forming a magnificent tail that points away from the solar furnace. This tail, composed of pristine material from another star system, is not a passive banner flowing in the solar wind. It is a directed beam, a shotgun blast of particulate matter, whose trajectory is dictated by the comet's own motion and the geometry of its orbit. The retrograde motion ensures that this stream of foreign dust does not gently accompany the planets in their orbit, but instead cuts across their paths like a blade, a phenomenon one might liken to a cosmic milling angle, dramatically increasing the probability of intersection with any object residing in that plane. The initial and most conservative level of analysis confirms that the gravitational perturbation is, indeed, insignificant. The dust is the agent. The comet's passage is not about push and pull, but about contamination and seeding. The fine particles ejected from 3I divided by Atlas, traveling at velocities commensurate with the comet's own hyperbolic speed, create a transient, ribbon-like cloud stretching along its trajectory. This cloud, though diffuse, represents a sudden, localized injection of foreign material into the interplanetary medium. While the nucleus of the comet passes a safe 30 million kilometers from Mars, as confirmed by ESA observations on the 3rd of October, the dust stream it generates is far wider and more pervasive. Could this ethereal river of dust, this ghostly signature of a distant star, be the true legacy of the visitor, a legacy written not in gravity, but in grit? Progressing to a second, more intricate level of deduction, we must consider the consequences of this geometric intersection. The dust stream, cutting across the ecliptic plane, does not simply exist, it interacts. Each particle, a microscopic world unto itself, becomes a potential micro-meteoroid. For a planet like Mars, with its thin, exposed atmosphere, this represents a subtle but measurable shift in its environmental context. The Martian sky, already regularly scoured by natural meteoroid falls, would experience a brief but statistically significant enhancement in the flux of incoming particles. These would not be the brilliant fireballs of larger impacts, but a silent, high-velocity rain, the sleet of interstellar material vaporizing in the upper atmosphere. This would create a transient, perhaps undetectable layer of metallic ions, a faint and fleeting atmospheric tattoo left by the passing visitor. Is the Martian atmosphere, then, not just a shield against space, but a canvas upon which the passage of interstellar objects can momentarily inscribe their signature? This leads to the third and most speculative tier of this hypothesis, the formation of a unique, temporary focus of dust and plasma in the solar wind upstream of Mars. The geometry of the encounter is such that for a period of hours or days, the planet would have passed directly through the densest part of this interstellar debris stream. The solar wind, that relentless stream of charged particles flowing from the Sun, would interact with this newly introduced dust. The impacts would charge the dust particles, creating a complex plasma environment. The magnetospheric and ionospheric systems of Mars, perpetually engaged in a battle with the solar wind, would suddenly be confronted with a new, alien component in that wind. Could this have created a brief, anomalous region in the space weather preceding Mars' awake within the solar wind's own wake? A subtle disturbance in the magnetic and particulate fields that the planet's scant magnetic cusps and its entire atmosphere were forced to respond to. The instruments orbiting the red planet may have registered unexplained fluctuations in charged particle density or subtle shifts in atmospheric escape rates, all traceable not to the comet's gravity, but to the geometric precision of its dusty trail. Thus, the legacy of 3I divided by Atlas may be far more nuanced than a simple catalogue entry of a passing rock. Its significance may be determined not by its mass or its gravity, but by the specific angle at which it crossed our planetary plane. The wetness of Mars, not in terms of water, but in its exposure to this cosmic drizzle, was not a function of proximity alone, but of orbital geometry. The visitor did not need to shake the planet to change its immediate environment. It merely had to draw a line through its sky. And so, we are left to ponder. If a single, small interstellar object can so subtly alter the material constituency of a planet's vicinity, through geometry alone. What does this imply about the long-term history of our solar system, which has undoubtedly been crossed by countless such silent travelers from the deep? What other invisible geometric legacies are written into the very fabric of our planetary space, awaiting only the right observer to decipher their origin? This contemplation of a single object's potential, however, inevitably draws our gaze back to its profound rarity, its status as a confirmed messenger from the void between stars. For 3I divided by Atlas, discovered on the 1st of July, 2025, by the vigilant eyes of the Atlas survey in Chile, is not a common sight. It is only the third such confirmed interstellar visitor to grace our telescopes, following the enigmatic 1I, Oumuamua in 2017, and the more conventionally cometary 2I divided by Borisov in 2019. Its detection triggered an immediate and coordinated response from the global astronomical community, with NASA and ESA activating their deep space tracking networks to capture every possible datum from its fleeting passage.